Hello. This is Nicholas, and I'll be deriving some pretty interesting properties about the Laplace transform. The first property I want to talk about is, let's say that the Laplace transform of f of t is some function in terms of s. Then, if I take the Laplace transform of e to the at times f of t, that's a bad bracket, at, that's going to just be f of s minus a. Oh, a chemistry assignment. So how can I prove this? It's really pretty simple. This right here is just the integral from 0 to infinity of e to the negative st times e to the at f of t dt, which is the integral from 0 to infinity of e to the negative s minus a t dt, and that is precisely f of s minus a, because where there was just an s in the original Laplace transform, there's now that s minus a. And so that can be, as I showed in the last video, really useful. The next property is the Laplace transform of f prime of t. It is, turns out, the integral from 0 to infinity of f prime of t e to the negative st dt. And so we integrate by parts, and we get f of t. We integrate that, and we keep e to the negative st evaluated from 0 to infinity, plus s times the integral from 0 to infinity of e to the negative st times f of t dt, which is, this whole thing just becomes negative f of 0, and that's plus s times the Laplace transform of f of t. So the Laplace transform of f prime of t is just this here. And this is what makes the Laplace transform so useful, is that if you've got a y prime and if you've got a y, see, this y prime or this f prime can be written in terms of the Laplace transform of the f plus or minus some constant. And so then the differential equation turns into an algebraic equation in terms of the Laplace transform, which is very nice. And it turns out that in general, and you can do this by induction on n to prove it, the Laplace transform of the nth derivative of t, of the function f, is s to the n times the Laplace transform of f of t, and now watch this, minus s to the n minus 1 f of 0, minus s to the n minus 2 f prime of 0, minus minus s to the 0, or just 1, times the n minus 1th derivative of f evaluated at 0. So any derivative, even if we had, say, a y triple prime plus a y prime plus a y, say 4e to the 3t, that's what I used in my last example, that can still be solved using the Laplace transform, because we can write any derivative, the nth derivative, when we take the Laplace transform on both sides, it's going to give us just the Laplace transform of y, or of f of t, times some scalar, and then minus a constant. All that stuff's a constant. And so you could solve for the Laplace transform of f of t, and then just undo it and get your y, or your f of t. So that's what makes the Laplace transform a very, very powerful tool for solving differential equations. Another property is if we've got the Laplace transform of an integral. Doesn't show up quite as much, but if I have, say, the integral from 0 to t of f of I'm using a dummy variable x dx, what I can do if I have that Laplace transform, I'm going to let g of t, and then it is a function of t because t is the upper bound of that integral. I'm going to let that be the integral from 0 to t of f of x dx. Then by the fundamental theorem of calculus, g prime of t is just f of t. So that would mean that the Laplace transform of f of t, which is really just a derivative, right? It's g prime of t, is s times the Laplace transform of g, which is this integral here, the integral from 0 to t of f of x dx. And we would have a minus, g of 0 here, technically. But g of 0 is the integral from 0 to 0 of whatever. So g of 0 is 0. And so in other words, the Laplace transform of the integral from 0 to t of f of x dx is just 1 over s times the Laplace transform of f of t. And so even integrals, you can still write in terms of the Laplace transform of the original function times some scalar, of course. And again, that is what makes them so useful. So hopefully this is a g of 0 because of the property up here where it's the original function here that we are considering its value of 0 at. In other words, not the derivative, the original function. So now another property is that it's kind of a peculiar property, but if I consider the Laplace transform of f of t, call that to be another function in terms of s, capital F, then I take the Laplace, that's not that good of an s, or of an L. If I take the Laplace transform of t to the n times f of t, then it turns out what I'm going to get is negative n to the n times the nth, partials yet, times the nth derivative of f with f is a function of f. I said f is a function of f. F is a function of s. The nth derivative of f with respect to s. So how could I show this? I'm going to start out with the definition of the Laplace transform. So f of s is going to be the Laplace transform of f of t, of little f of t, which is the integral from 0 to infinity of e to the negative st times f of t dt. If I differentiate both sides, that means that with respect to s is this. And now I'm gonna use another rule from Calc 3, and the rule is known as Leibniz. I think that's it, Leibniz rule for differentiation under the integral sign. You might have heard it called Feynman's trick, even though it was Leibniz who really came up with it first. And then Fineman just said, well, it's a pretty cool trick, but it was Leibniz. Anyway, it says that, and you've done this before. It's just a more general case, the Leibniz rule. It says if we're differentiating an integral. And the integral is with respect to another variable. See, here we're differentiating with respect to s, but the integral is with respect to t. So we can't just cancel out the derivative and the integral like we could where we had before the integral from 0 to t of f of x dx, and we took the derivative with respect to x of that. In that case, we just got f of t. But here, what the Leibniz rule for integration says is that we can make this the integral from 0 to infinity of the partial derivative with respect to s of e to the negative st times f of t dt. And that intuitively, that's just always kind of made sense to me. In other words, you differentiate with respect to s, well, under the integral sign, just everything that has an s, differentiate that, and everything that doesn't, you treat it as a constant. That's what the partial derivative is saying. And here, actually, you're using that rule too. You're making it the integral from 0 to t of the partial with respect to x of f of x dx, and that becomes the integral from 0 to t of f prime of x dx, and then that becomes there, since the derivative and the integral undo each other, that's just f of x evaluated at t and 0, which gives us the f of t, and we assume f of 0 to be equal to 0. So you've used this rule before, you just haven't really realized that it's a general case of the more specific differentiation of the integral. And so now we can make this the integral from 0 to infinity of, and now the f of t dt, that's a constant with respect to s. So we get a, put the negative out front, negative s e, or I'm sorry, negative t e to the negative st times f of t dt. And so now what I can do is say that this right here is just the negative of the Laplace transform of t times f of t. And so the more general rule that I stated here holds at least for n equals 1, right? Because the Laplace transform of t times f of t was just I just stuck a negative out front and then differentiated what was inside here, and I got this negative out here. So as an example, let's say I wanted the Laplace transform of t e to the 2t. What I could do is I could recall that the Laplace transform of e to the 2t is 1 over s minus 2. And then I could say I'm multiplying, this is really t to the 1, so that means that the Laplace transform of t e to the 2t is negative 1 to the 1 times the first derivative with respect to s of 1 over s minus 2, which is negative of the derivative with respect to s of s minus 2 to the negative 1. The negative and the negative are going to give us a positive, and we're going to get 1 over s minus 2 squared. And that's the Laplace transform of t e to the 2t. So, and how you could show this property holds true in general is you could say, well, it obviously holds for the base case. I just showed that. So then what you could do is differentiate again, right? Or you would assume that it is true for the n minus 1th case, and then you could prove it by induction on the nth case. So you'd be inducting on n, just like how you did before. And the idea, you just write the nth case in terms of the n minus 1th case. I should probably do an example of, what property was it? Well, I don't think I have any other examples to. I could maybe just show you this. Let's say sometimes you have to use trig identities with these things. If I had, say, the Laplace transform of the sine of 3t times the cosine of 3t, I can make it 1/2 the Laplace transform of the sine of 6t, which is 1/2 times, now the Laplace transform of sine of 6t, that's going to give us a b is equal to 6 here, so 6 over s squared plus 36, or in other words, 3 over s squared plus 36. And I think that takes care